Hi, this is Michel Birler. This video belongs to a series about common mistakes in discrete choice modeling. We will talk about significant and insignificant parameters. When you estimate a discrete choice model, the first thing you do is probably to look at the sign of the estimated coefficients. And the second thing you do is probably to look at the t-test. And you like your parameters to be significant. It means that the value of the t-test should be higher in absolute value than 196. And a common mistake is to remove from the model all parameters such that the t-statistic is less than 196. This is not correct, and we will explain why. This example is a transportation mode choice model with two alternatives. It's a binary logit model with the classical variables travel cost, travel time, and number of transfers for the rail alternatives. In the estimation report, we observe that two of the betas, beta time rail, which is the coefficient for travel time of the rail alternative, and beta transfers, which is the coefficient of the number of transfers for the rail alternative, have a t-test which is less than 196 in absolute value. The point that I want to make is that it is not valid to simply and blindly remove these two variables from the model just because the coefficients have a t-test which is less than 196. So let's see why, and let's see also what needs to be done. So let's look at the t-test first. The output of the estimation for beta time rail is minus 0.499 for the value of beta, and the standard error is estimated to be 0.419. These are the two values that I use to calculate the t-test. When we perform a t-test, we are actually testing an hypothesis called the null hypothesis, and most of the time denoted by H0. In the context of a t-test, the null hypothesis is that beta, the true value of the parameter, is equal to 0. In this case, the t-test is equal to minus 1.19. The fact that it is in absolute value less than 196 implies that we cannot reject the null hypothesis at the 5% level. However, in this specific case, the hypothesis itself does not make sense. Indeed, in the context of a transportation mode choice model, we know that the true value of the beta time rail, so the coefficient for the travel time, is not 0. There are plenty of evidence in the literature, so testing this hypothesis does not make sense. To take another example, we could have tested the hypothesis that beta equals 0.1. This hypothesis does not make sense either. Well, first, it's positive, and we assume that the beta coefficient for travel time is negative, because when travel time increases, we expect the utility to decrease. And then 0.1 seems to come from nowhere. It's arbitrary. However, when we test this hypothesis, we obtain a t-test of 0.239, which implies that we cannot reject the hypothesis. But it does not mean that we need to accept it. Indeed, this hypothesis does not make sense, and it's not because the test does not reject it that we will accept it. So the same is true for the hypothesis beta equals 0. It does not make sense, and the fact that it cannot be rejected does not mean that we should accept it. So the first recommendation is to avoid testing an hypothesis that does not make sense. However, it's not always clear-cut like this. If we take the other example of the beta time transfers coefficient, the estimated value is minus 0.265, and the estimated standard error is 0.277. So in this case, the null hypothesis again is beta equals 0, and when we apply the test, the t-test is equal to minus 0.96. Therefore, we cannot reject the hypothesis. In this case, does the hypothesis make sense? Well, maybe, maybe not. But in any case, it makes sense to test it. Before making the decision to keep the variable or not, we need to consider the impact of this decision. Let's see what it means. When we do hypothesis testing, there is always possibility of errors. The classical terminology identifies two types of errors, denoted by type 1 error and type 2 error. A type 1 error occurs when the null hypothesis is rejected and it is true. The type 2 error occurs when the null hypothesis is accepted and it is false. In the context of our specification testing, a type 1 error would occur when we include an irrelevant variable. So we reject the hypothesis that the coefficient is 0, so we keep the variable. And the fact that h0 is true means that in the true model, the variable does not play a role. Similarly, a type 2 error happens when we omit a relevant variable, because we accept h0, so we accept the fact that beta equals 0, but h0 is false, so the true value of beta is not 0. The consequences of the model are different. If we include an irrelevant variable, we lose efficiency. It means that the estimates have a larger variance. If we omit a relevant variable, we obtain a specification error, and the potential damage is much bigger. So in terms of damage or cost, we will denote by C1 the cost of making a type 1 error, and by C2 the cost of making a type 2 error. And in the context of specification testing, the cost of a type 2 error is much bigger than the cost of a type 1 error. So let's measure the impact of an error. To do this, we calculate the probability to make an error. The probability of a type 1 error is equal to the probability that the null hypothesis is rejected, given that it is true, times the probability that it is true. The usual notation for the probability that h0 is rejected given that it is true is alpha. This is actually the level which is used for hypothesis testing. So if you decide that alpha is equal to 5%, then you get the threshold of 196 that is usually used in t-tests. And let's denote by lambda the probability that the null hypothesis is true. We can do the same for a type 2 error. It is the probability that h0 is accepted given that h0 is false times the probability that h0 is false. In general, the probability that h0 is accepted given that it is false is denoted by beta, and the probability that h0 is false is 1 minus lambda. From this, we can calculate the expected cost of an error. It is the probability of a type 1 error times the cost of a type 1 error, plus the probability of a type 2 error times the cost of a type 2 error. Using our notations, we obtain alpha lambda times C1 plus beta 1 minus lambda times C2. In the context of classical hypothesis testing, usually we have a strong belief in h0, which means that lambda is close to 1. And the cost of a type 1 or type 2 error are similar. So in this case, it makes sense to prefer small alpha, typically 5%, and sometimes 1%. But in the case of specification testing, which we are actually applying in the context of discrete choice, well, first, we don't have a strong belief in h0. So in this example, let's take lambda to be 0.5 to express the fact that we don't know. And as we discussed before, the cost of a type 2 error is much bigger than the cost of a type 1 error. Consequently, in this case, it makes sense to use larger alphas in order to perform the test, because the expected cost will be lower. So therefore, the magic value of 196 does not necessarily apply here. Well, it's difficult to recommend a specific value. It depends on the application, it depends on your belief in H0, it depends on the type of specification that you have. But there is absolutely no obligation to use alpha equals 5% and to use the threshold of 196. So the second recommendation is that you want to anticipate the impact of the test when you apply it. Okay, at this point, basically I told you that 1, you may not use the test at all if it does not make sense, and 2, you may use the test with a larger alpha, so to reject the hypothesis with more flexibility. But still, it's not because we don't want to apply the test that there is no issue in the model. The fact that we have low t-test is actually a consequence of the fact that we have high standard errors on the estimates. Now the question is, does it matter? Is it important? Well, in order to do that, you want to calculate confidence intervals. Let's take our choice model. So the choice model predicts for individual n the probability to choose alternative I, given the explanatory variables xn and the set of parameters theta. And because we estimate theta using maximum likelihood, the estimates follow asymptotically a normal distribution with mean theta hat and a variance-covariance matrix, sigma hat. And now we need to use the model for something. So we want to calculate indicators. So let's take the classical example of the market shares. So if you want to calculate the market share of alternative I, we calculate the average value of the choice probability over the population. Of course, in practice, we use sample enumeration, but let's look at this value for now. Now, how do we calculate the confidence interval? We use simulation. So we draw realizations of theta from the normal distribution with mean theta hat and variance-covariance matrix sigma hat. And for each realization of theta from this distribution, we calculate the indicator Wi. Okay, so we obtain a series of realizations of the Wi. And what we do is that from these empirical values, we calculate, let's say, the 5% and 95% quantiles of these values. And we obtain the 90% confidence intervals for Wi. So let's go back to our example and let's look at the market shares for the rail alternative. What we obtain in this example by simulating the sample is a value of 35.5% market shares for the rail alternative. And if we look at the 90% confidence interval, which is obtained by the simulation technique that I just described, we see that the confidence interval is between 25.7% and 46.7%. Now the question is that, is this interval small enough for our purpose or not? And again, it depends on the application. It may be too wide, and in this case, we need to do something about it. So the recommendation here is to calculate confidence intervals to see if the precision that you have in your model is sufficient for the application that you have in mind. Now, if it is not sufficient, if you still have an issue of precision, what do you do? Again, the low t-test is due to the fact that we have high standard errors. What is the cause of these high standard errors? Well, there are several possible reasons. One is that you have an insufficient amount of data. Another possibility is that the variability of the data is insufficient. For example, if the travel time is exactly the same for all individuals in the sample, there will be no way to estimate a travel time coefficient. So what are the solutions? Well, of course, if you want more precision, the best thing to do is to collect more data. However, it's not always possible. So in this case, you may want to modify the specification. So let's look at our example again. In our example, we have 6 parameters. We have the cost and the time coefficients that are alternative specific. We have the alternative specific constant for car, and we have the coefficient of the number of transfers. In order to change the specification, what we can do is to assume that the value of time is constant for the 2 alternatives. So it means that the beta time car coefficient can be written as the product of the beta VOT, which is the value of time, and the beta cost car, which is the coefficient of the cost for the car alternative. Similarly, the beta time rail, so the coefficient of the travel time for rail, can be expressed as the product of the beta VOT and the beta cost rail. So by doing this, by including this additional assumption, I have reduced the number of parameters from 6 to 5. So now if we look at the estimation of this new model with 5 parameters, we observe that the value of beta VOT, which is here 16.2, is associated with a large t-test. In any case, a t-test which is larger than 196. In this case, it's 355. So we can reject the hypothesis that the true value of VOT is equals to 0. So we don't have the issue associated with the time coefficient anymore, because the time coefficient is the product of two significant parameters. The last recommendations are that we want to collect more data and or improve the specification. So let's summarize the recommendations that have been listed in this video. First, you do not want to test an hypothesis that does not make sense. 2, when you make an hypothesis testing, you want to anticipate the impact of the decision you will make based on this test. If you have low precisions in your estimates, so high standard errors, you need to calculate confidence intervals in order to check if the result is acceptable or not. If it is not acceptable, you need to collect more data and or improve the specification of the model.